In the tapestry of scientific thought, few figures loom as large as Sir Isaac Newton. Born in England in 1643, Newton was a true polymath, his genius leaving its mark on mathematics, optics, and, most profoundly, physics. It was Newton who unveiled the fundamental laws that govern the motion of objects, forever changing our understanding of the universe. Before Newton, the world grappled with a hodgepodge of theories about motion, often rooted in superstition and lacking empirical evidence. Aristotle, for instance, believed that objects had an inherent tendency to reach a state of rest, an idea that persisted for centuries. Newton, however, dared to challenge these long-held beliefs, embarking on a quest to unravel the true nature of motion. His magnum opus, the Philosophiae Naturalis Principia Mathematica, published in 1687, laid out his revolutionary ideas. In this monumental work, Newton presented his 3 laws of motion, a set of principles that would become the cornerstone of classical mechanics. These laws provided a unified framework for understanding the motion of everything from apples falling from trees to planets orbiting the sun. Newton's contributions extended far beyond his laws of motion, including the development of calculus and significant contributions to our understanding of gravity. Newton's first law of motion, often referred to as the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction, unless acted upon by an unbalanced force. This law might seem counterintuitive at first, as we're used to objects slowing down and coming to a stop. However, this is because forces like friction and air resistance are constantly acting upon them. Imagine a ball rolling across a perfectly smooth, frictionless surface. In this idealized scenario, the ball would continue rolling forever, at the same speed and in the same direction, because there are no forces to slow it down or change its direction. This is the essence of inertia, the tendency of an object to resist changes in its state of motion. When a car suddenly accelerates, our bodies tend to stay at rest, pressing us back against our seats. Similarly, when a car brakes abruptly, our bodies continue moving forward, which is why seatbelts are crucial for safety. Newton's second law of motion builds upon the concept of inertia, providing a mathematical relationship between force, mass, and acceleration. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. In simpler terms, the harder you push an object, force, the faster it accelerates, and the heavier the object, mass, the slower it accelerates under the same force. This law can be represented by the famous equation F equals sine ma, where F is the net force, m is the mass, and a is the acceleration. Consider the example of pushing a shopping cart. If the cart is empty, low mass, a small amount of force will cause it to accelerate quickly. However, if the cart is full of groceries, high mass, you'll need to apply a much larger force to achieve the same acceleration. The second law of motion is ubiquitous in our daily lives. From the force required to lift a book to the power needed to accelerate a car, it helps us understand why some objects are easier to move than others and why it takes more force to stop a heavy object than a light one. Newton's third law of motion states that for every action, there is an equal and opposite reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. These two forces are called action and reaction forces, and they always occur in pairs. Imagine jumping off a small boat onto a dock. As you push off the boat pushes back on you with an equal and opposite force. This is why the boat moves backward as you jump forward. Another example is the recoil of a gun. When a gun is fired, the expanding gases from the burning gunpowder exert a force on the bullet, propelling it forward. At the same time, the bullet exerts an equal and opposite force on the gun, causing it to recoil backward. Newton's third law of motion is crucial for understanding a wide range of phenomena, from the propulsion of rockets to the stability of structures. Newton's laws of motion are not confined to textbooks and laboratories. They are constantly at play in our everyday lives. From the simple act of walking to the complex maneuvers of airplanes, these laws govern the motion of objects all around us. Consider the act of walking. When we walk, we push backward on the ground with our feet. According to Newton's third law, the ground exerts an equal and opposite force on our feet, propelling us forward. This forward force is what allows us to walk. Another example is the flight of an airplane. Airplanes are able to fly because of the upward force generated by their wings, known as lift. This lift force is created by the shape of the wings and the angle at which they meet the oncoming air. These are just a few examples of how Newton's laws of motion are at work in our everyday lives. Newton's laws of motion are not limited to our earthly realm. They extend far beyond our planet, governing the motion of celestial objects throughout the cosmos. From the orbits of planets to the collisions of galaxies, these laws provide a framework for understanding the grand dance of the universe. Newton's law of universal gravitation, which states that every object in the universe attracts every other object with a force proportional to their masses, and inversely proportional to the square of the distance between their centers, is a direct consequence of his laws of motion. This law explains why planets orbit stars, moons orbit planets, and galaxies cluster together. Newton's laws also play a crucial role in our understanding of space travel. Rockets are able to escape Earth's gravity and travel to other planets by expelling propellant at high speeds, creating a force on the rocket, propelling it in the opposite direction. By applying Newton's laws of motion, we can calculate the trajectories of spacecraft and predict the orbits of comets. Sir Isaac Newton's contributions to science, particularly his laws of motion, stand as a testament to the power of human curiosity and ingenuity. His work revolutionized our understanding of the physical world, providing a unified framework for explaining the motion of everything from apples falling from trees to galaxies swirling through the cosmos. Newton's laws are not merely abstract concepts confined to textbooks. They are fundamental principles that govern our everyday experiences and shape our understanding of the universe. From the simple act of walking to the complex maneuvers of spacecraft, these laws are constantly at play, shaping the world around us. While Newton's laws have been refined and extended by later physicists, particularly in the realms of relativity and quantum mechanics, they remain the cornerstone of classical mechanics. His legacy continues to inspire generations of scientists, reminding us that the universe, for all its complexity, operates according to elegant and comprehensible laws.